Hello, everyone. Yeah, this is the second paper presentation. The title is Under-Reported Security Defects in Kubernetes Manifest. The presenter is Akond Rahman. He's an assistant professor at Tennessee Tech University. His research interests include DevOps and secure software development. He got his PhD from North Carolina State University. He won the many awards such as ACM Sig South Doctoral Symposium Award, and the Distinguished Paper Award, and so on. He actively collaborates with industry practitioners from IBM, Siemens, and others. So please welcome the accounts for his presentation. You can start your presentation.
Thank you. Hello, everybody. Greetings. I am Akant from Tennessee Technological University, and I welcome you all to our presentation titled Underreported Security Defects in Kubernetes Manifests. This work was partially funded by the U.S. National Science Foundation, and the first author is Dibyendu, and the co-author is Shazibul. Most of the work was done by Dibyendu. Unfortunately, he couldn't be here for unavoidable reasons, and I will be presenting on behalf of him. So before I dive into the details of the paper and what we did and what we found, I would like to give you a brief introduction on what Kubernetes is. It is an open source software for automatic management of computerized services such as containers. Initially, it was developed by Google in 2014. And their idea was whatever they have done over the years to orchestrate their containers. That means how to use containers at scale so that applications can be rapidly deployed and tested, and if needed, fixed, and so on and so forth. To bring that experience into one product, and then they basically just open sourced it, and which is now being used by many users. The project is now maintained by the Cloud Native Computing Foundation since 2015. Before I dive into what Kubernetes manifests are, this is what a typical architecture diagram of any Kubernetes installation. So on your left-hand side, you have users who uses manifests to specify what configurations they should have for Kubernetes. And then that is being executed through a terminal called kubectl, command, I should say, called kubectl. And then once those configurations which are specified as manifests are executed, under the hood, a lot of things happen. So you have your scheduler, API server, and controller, which are all used to control the kubelets and pods and containers. So if you look into our paper, you will get more details and background on what Kubernetes is. However, the focus of this particular paper is on Kubernetes manifests. So this is basically some pre-formatted file, typically in YAML, which has a specific syntax and has semantics. So as you can see, it has some special keywords that mean something for orchestrating containers and so on and so forth. So, for example, in this particular case, we see that there is something called a pod, which is being specified, which says that for this particular pod, I will need containers with the name CPU, demo, CTR, and it will have one CPU resource. And we wanted to understand if these particular manifests that are typically used to specify what the Kubernetes installation should look like can have, is it possible for them to have security problems like vulnerabilities or security bugs or regular bugs in general? And there is a motivation for that because this particular product, Kubernetes, is being used by so many companies across the board. So you have IT organizations like Sling, Spotify, Pinterest, the US Department of Defense, then Adidas. They all use this particular product to orchestrate their applications, to manage and deploy their applications. And not only they have used this particular product to increase their release frequency of software, for example, reduce it down from 4 to 6 weeks to 3 to 4 times a day, it also has helped them to manage their installations and applications. But what motivated us to conduct this particular study is despite all these benefits and despite being a very mature products, and because it was initially developed by Google and now it's maintained by the Cloud Native Computing Foundation, people, practitioners who use this particular software project called Kubernetes, they do have experienced security incidents. So in this particular survey, the 2020 StackRock survey, 90% of the total participants reported that they have encountered at least one insecurity incident in last 12 months before the survey. And then this particular perception is later on and is sometimes manifested into large-scale security breaches. For example, Tesla, who uses Kubernetes, was susceptible to an attack, namely a cryptocurrency mining malware attack, where malicious users used Tesla's AWS resources for cryptocurrency mining. And that happened because of insecure Kubernetes configuration, which typically resides in Kubernetes manifests. So all these examples, both coming from in forms of survey, then also in forms of concrete real-world attacks, motivated us to study if security related problems can appear in Kubernetes manifests. And the goal is to gain an understanding if, first of all, if security bugs, security defects appear, like vulnerabilities appear, and to what frequency do they appear. If they appear in high frequency, then we need immediate action. If they are underreported or have not been studied thoroughly, then as a research community, we might need some more rigorous effort, or maybe look into the same thing in a different angle. So prior research has mostly focused on how Kubernetes can be used to create a wide variety of systems that is typically used for high performance computing, machine learning. There are also case studies on Kubernetes related to performance and resource management. We have discussed these types of related work in our paper. And based on by looking at the existing work, we felt like there is a possibility to systematically study if security bugs appear in Kubernetes manifests. So we answered the following research question: how frequently do security defects occur in Kubernetes manifests? So what we did was we looked into open source. So we systematically mined GitLab repositories, we curated them, and then we applied qualitative analysis, where basically two raters. So the first author, and we also had a volunteer rater who looked into the commit messages for each of the Kubernetes manifests and tried to understand if a developer or multiple developers who modified that particular manifest had some security specific keywords in them. So our first activity was, like I said, there were two raters, and both raters actually observed the presence of keywords in the commit messages that we got from prior work. So prior work conducted by Bose et al. In their FSC paper, they used a set of keywords to find out if security vulnerabilities appear in code review, like code review reports, like issue reports or Jared code reports. So we took those keywords, applied them in the case of commit messages, and then we filtered out a set of commits for which those keywords appear. And then both raters who do have experience in secure software development and software development in general looked into each commit message to see if the message itself expresses an action that violates confidentiality, integrity, or availability, the CIA triad. If it does, then it's labeled as insecure. Otherwise, it's labeled as neutral. Then we calculate Cohen's kappa to measure the inter-rater reliability agreement. So we came up with a data set with 38 repositories, which had around 1,800 Kubernetes manifests, and which were modified in 5,000 commits. So both raters had to look into these 5,000 commits one by one to find out if security defects are reported in these particular commits. The surprising result was that we didn't find a lot of commits where developers have expressed an action related to a security. So according to our qualitative analysis, out of the 5,000 commits, only 41 were labeled as insecure by our two raters. And those 41 commits were used to modify 39 Kubernetes manifests. So, and we use our proportion of security defect metric to see that it's well around, it's less than 1%, indicating that when it comes to self-reporting as expressed by commit messages by developers, security defects are rare for Kubernetes manifests. So our hypothesis, based on our findings, our hypothesis is that it is possible, number one, that the data set that we have looked into is not big enough. And obviously, we need to study more data sets, possibly by mining GitHub and other open source repositories. It is also possible that developers themselves are not well aware of the possible security consequences that Kubernetes manifests have, and that is why it is underreported. So the reason we make this particular conjecture is basically comes from our results and also some best practices that we identified as part of our SecDev 2020 paper. And while the raters were analyzing the commit messages, they did find examples where Kubernetes-related security best practices were violated in the manifest themselves. So based on these two pieces of evidence, we conjectured that the data that we are seeing in less than 1% of the security defects being related to commit messages, with less than 1% of the commit messages being related to security defects might be underreported. And we feel like there is a lot of scope of opportunity to systematically study the vulnerabilities and security defects in Kubernetes manifests. And also there is also scope. So once that is established, then there is also scope of like, what are the root causes? Like, why do they appear? Is it more of an issue related to awareness and education and training, or is it possible that because of the way Kubernetes is used to orchestrate hundreds and thousands, is it likely that the attack surface is too much, and like our keynote speaker said today, it is important to consider design issues when it comes to design issues and architectural issues when it comes to mitigating vulnerabilities and security defects. So all in all, we do feel that our findings can lay some groundwork to do more interesting research. From a scientific perspective, our contribution is that we have came up with a curated data set of security defects. So basically, it's a CSV file where you have all the files and the repositories listed, and for each Kubernetes manifest file, there is a label of insecure or neutral. And then we also have we have done an empirical analysis of how frequently security defects appear in Kubernetes manifest. So from that perspective, we do contribute some to the existing Kubernetes-related literature. Limitations include rater bias. So this is a qualitative study, and like any qualitative study, there is possibility of rater bias where the raters have their own subjective judgment, and they apply it and they bring it to the qualitative analysis. We mitigated this by doing using two raters and doing and we also calculated the inter-rater reliability to be, and we found that it's substantial. The data collected was from GitLab, so because this was more of an exploratory study, we looked into GitLab repositories and not GitHub. Moving forward, we would like to do that for GitHub as well. And also, when we identified the security-related comments, we use keywords. We use keywords to at the first as part of our first activity, which could be limiting. So, because this is actually we might not capture all the security defects because we were confined to our set of keywords. So in short, Kubernetes is an emerging platform that is gaining more and more interest among software practitioners. Software practitioners all across the board, from government, industry, and academia, are using this particular technology to orchestrate and deploy their applications and manage their containers. However, there is a need to study the security bugs or vulnerabilities that appeared in Kubernetes manifest. So we did a qualitative analysis where we mined open source repositories, and then we found out that the reported security defects as expressed by commit messages is very low, which gives us the motivation to do more exploration, to systematically study if this number holds and find out why security bugs appear in Kubernetes manifest in the first place. So with that, I would like to conclude my presentation, and I'm open for any questions.
Okay, thanks for the interesting talk. Ricardo left one question: to what extent underreported security defects are depending on the community? So he means that does community means less non-reported defects, or is it dependent on the importance of the company behind it? Maybe you do not have data, but yeah. So do you have any answer for that?
Yeah, I think this is an excellent question. I think the question actually alludes to to our future steps of trying to identify the root causes. So there are two things that we need to tackle if we want to answer that question properly. That is, number one, look into a bigger data source. Number two, identify if the reported security defects that we have, is it actually underreported? It is possible that if you look into another data source, we will get more. The number might jump up. And once we have that baseline, then we can start asking questions by looking into software artifacts, mining software artifacts, and also by contacting developers. Like, do you feel like this is you have violated us? There's a security vulnerability here. Do you agree with it? If you don't, why don't you agree with it? What is the context? Why did you think? Why did it appear in the first place? And so on and so forth. So if this, I feel like our short paper, this particular short paper gives us more motivation and foundation to do more interesting work that will answer questions like that.
Can you elaborate a bit more for the subject, the repositories you selected? Were there any criteria to select those repositories, or are there any characteristics of the target 38 repositories? Yeah.
Yeah, thank you. So in the mining software repositories community, it's kind of established that if you are downloading open source repositories, you need to do filtering. So we applied the following filtering criteria. First of all, the repository is not a clone, so it's not it didn't copy another repository, so that we identify projects that are not used for personal purposes. It has at least 10 developers. It has a lifetime of, say, 1 year. Then it has at least 2 commits per month to get an understanding if that repository is being updated regularly. And on the top of my head, those are the criteria that I can think of. But people do apply other types of criteria as well. So in our case, for example, we also looked into how many YAML files they have, because it is possible that a repository only mentions Kubernetes, but it doesn't actually upload the artifacts necessary to do Kubernetes-related research. So, and it is also, someone can actually look into the number of issues. Someone can also look into the raw number of commits, and so on and so forth. So if you look into our paper, I think you'll get a more concrete and a systematic answer than what I just gave.
Thank you. And I have one more question. Even though the number or the portion of the security defect you found is small, but how was the expected impact? Even though it's a quite small security problem, may quite big problem. So did you find any, how can I say, some qualitative difference between the finding?
So yeah, again, thanks for the great question. So one limitation of our paper is that we do look into commits, which does not actually capture the entire context of a bug or a vulnerability. So moving forward, so in our set of repositories, we didn't find too much of information where a commit message actually mentions a bug report or a vulnerability report. So we didn't get that information. But hopefully, if you look into some more established data source like GitHub, where people do actually link commits to issues, bug reports, and vulnerability reports, I think we will get even more context, and we will be able to answer like how severe are these security bugs.
Thanks. Yeah, I think this worked as an initial stage, so it can be extended further, various ways. So I expect to see more your future work later. Yeah. Okay, then I think if there is no further questions, we can close this presentation. So thanks for your talk. And then if anyone have a question or comments, you can go to the discussion room after this session. Yeah, thanks again.
Thank you.